Do you believe a device could generate thrust using only electricity with no fuel and no visible reaction force? That is the controversial claim made by Charles Buhler, a former NASA engineer who worked on space systems that demand extreme precision. This technology is described as having the potential to change how satellites operate, how rockets move, and even how power is balanced in space. If that is true, it would challenge the way we understand and apply Newton's third law, one of the foundations of modern physics. Stay with this video until the end to see what is really happening and why scientists remain skeptical yet feel compelled to take this invention seriously. The controversy begins with a claim that sounds simple, yet deeply unsettling to modern physics. A device is said to generate thrust using only electricity, without burning fuel, without ejecting mass, and without any visible reaction force. In space science, this is not a small detail, because every propulsion system we know depends on pushing something away. Rockets move forward because they throw exhaust backward, and satellites adjust their paths by releasing propellant in controlled bursts. This basic idea is taught early, repeated often, and trusted completely. That is why this claim immediately triggered alarm bells across the scientific community. According to the description, the system does not rely on air, plasma, ions, or gas. It does not use rotating parts, vibration, or hidden jets. Instead, it is described as a closed electrical system where force appears without anything leaving the device. If taken at face value, this challenges how motion is expected to behave in a closed system. What makes the claim harder to ignore is that it is not presented as a one-time anomaly. The reported behavior is described as repeatable under certain conditions. The effect is said to appear again when the same setup is used and disappear when conditions change. This pattern matters because randomness is often the signature of experimental error. Repeatability suggests structure, even if that structure is not yet understood. Still, repeatability alone does not equal truth. Science has seen many effects that looked consistent at first, only to collapse under deeper inspection. Small forces are especially dangerous because they sit at the edge of measurement accuracy. Thermal expansion, electrical leakage, vibration, and electromagnetic coupling can all mimic thrust. These effects can remain invisible until experiments are redesigned with extreme care. That is why the claim sits in a narrow and uncomfortable space. It is large enough to demand attention, but small enough to raise suspicion. The idea also touches a deeper nerve within physics. If a system can accelerate without pushing against anything external, then momentum seems to appear from nowhere. That would not only affect propulsion, but also the rules used to describe motion itself. Such implications force scientists to slow down and examine every assumption. The community response so far has not been excitement, but controlled caution. Researchers are trained to ask where the hidden interaction might be. Is the system truly closed? Is it exchanging momentum with an electric field, a structure, or an environment that has not been fully isolated? These questions do not accuse dishonesty. They reflect hard lessons learned from past failures. What keeps this claim alive is not belief, but discomfort. It refuses to disappear with a simple explanation. It also refuses to prove itself beyond doubt. That tension is the heart of the story. Before debating motives, personalities, or future impact, the focus must remain on the claim itself. Understanding what is being asserted and why it unsettles established thinking is the first step. Only after that foundation is clear does it make sense to look at who is making the claim and why their background caused scientists to listen instead of laugh. At the center of this investigation is Charles Buhler, a figure whose personal history adds weight to a claim many would otherwise dismiss. Public information about Buhler's early life is limited, which is common for engineers who spent most of their careers outside the public spotlight. What is known is that he was born in the United States and built his professional life far from media attention, focusing instead on technical work that values precision over publicity. This quiet background matters because it frames him not as a personality driven by fame, but as someone shaped by long years inside demanding technical environments. Before his current work, Buhler spent a significant part of his career connected to NASA programs, where systems are designed under extreme constraints and where failure carries real consequences. In those settings, engineers learn to distrust easy explanations and to treat unexpected results as potential threats rather than breakthroughs. His work often involved electrostatics and highly controlled physical systems, fields where invisible forces can influence outcomes in subtle but critical ways. That experience trained him to look closely at interactions most people never think about, especially forces that do not announce themselves clearly. This background helps explain why Buhler's later observations did not immediately get dismissed by his own team as noise or error. Leaving behind a stable career path to pursue a controversial idea is not a common move in aerospace engineering. Reputation in this field is built slowly and can collapse quickly, especially when someone steps near claims that appear to challenge long-standing physical rules. By choosing to continue this work openly, Buhler accepted the risk that his professional credibility could be questioned. He did not make that choice alone. His research became part of Exodus Propulsion Technologies, a small group of engineers with backgrounds in aerospace, defense, and advanced electrical systems. This is not a company built around fast announcements or dramatic demonstrations. Their progress unfolded over years of testing, adjustment, and internal debate, which suggests caution rather than confidence. According to available statements, their focus was not to announce a finished engine, but to determine whether a physical effect was being misunderstood or overlooked. That approach separates investigative research from technological hype, even if the claim itself sounds extraordinary. Still, experience does not replace evidence. In science, background determines who gets heard, not who gets believed. Buhler's history does not prove the device works, but it prevents the discussion from ending at the first sign of discomfort. It forces attention to shift away from personality and toward mechanisms, measurements, and assumptions. This shift sets the stage for the next part of the story, where the focus moves from the person behind the claim to the features that make this idea appear different from the many propulsion concepts that failed before. This idea stands out because it does not rely on the same tricks that caused many earlier propulsion projects to fail. In the past, most attempts at propellantless propulsion still depended on something familiar, even if it was hidden at first. Some designs used special shapes, hoping geometry alone could push an object forward. Others focused on microwaves or vibrations inside a closed chamber, assuming energy could be directed in one direction. Many experiments later turned out to interact with air, heat, magnetic fields, or electrical leakage in ways the designers did not notice. Once those hidden effects were removed, the thrust vanished. The approach behind Charles Buhler's work moves away from all of that. Instead of shape, sound, or motion, it focuses on how electric fields behave inside solid materials. Electric fields are invisible forces created by electric charge, and in daily life, they usually seem weak and harmless. But inside carefully designed systems, electric fields can create pressure, stress, and stored energy. The key idea is that electric pressure does not always spread evenly. When different materials react differently to electric charge, the field can become unbalanced. This imbalance is similar to how air pressure can push harder on one side of an object than the other. In this system, the pressure is not made of air or gas, but of electric force. According to the research team, if this electric pressure is shaped correctly, It can create a small but consistent push in one direction. The push does not come from throwing anything away. It comes from how charges inside the material resist and respond to stress. This is where the design separates itself from old asymmetric capacitor experiments. Earlier capacitor systems used free charge moving through space, which often produced ion wind or electrical leaks. Those effects created the illusion of thrust, but depended on the surrounding environment. Buhler's team claims their system relies more on bound charge. Bound charge is locked inside the material and cannot drift away easily. Because of that, it behaves more slowly and more predictably under electric stress. This reduces interaction with air or nearby objects and makes testing cleaner. Another important difference is the goal of the project. This work is not trying to show large thrust or dramatic motion. The focus is on repeatability and control. The team wants to see whether the same behavior appears again and again under the same conditions. That is a cautious approach, and it is rare in a field known for bold promises. By avoiding claims of instant performance, the project shifts attention toward understanding the mechanism itself. If the effect disappears under stricter testing, the idea ends quietly. If it remains, then something deeper needs to be explained. The real importance of this work is not what it can do today. It lies in what it suggests about forces we may not fully understand yet. By focusing on internal electric structure rather than external reaction, this idea opens a small crack in traditional thinking. That crack leads directly into the scientific debate about whether such a system can exist without breaking the laws that define motion. This is the point where the discussion moves beyond personalities and design choices and enters the core of modern physics. The controversy exists because the claimed behavior of this system appears to collide with rules that have guided motion for centuries. One of those rules is Newton's third law, which states that every action must have an equal and opposite reaction. In practical terms, this law explains why rockets must throw mass backward in order to move forward. It also explains why engines, jets, and even simple recoil all behave the way they do. Closely tied to this is the principle of conservation of momentum, which says that the total momentum of a closed system cannot change without interaction with something outside that system. Together, these ideas form the backbone of how scientists understand movement in space. The problem arises when a system claims to produce thrust without pushing against anything external. If a device is truly closed and still accelerates, then momentum appears to come from nowhere. That is not just surprising, it is deeply uncomfortable for physics. This discomfort is not emotional but structural, because it threatens the consistency of many other laws built on the same foundation. Scientists immediately ask whether the system is truly closed or whether an interaction has been missed. History shows that missed interactions are common. Heat expansion, magnetic coupling, vibration, electromagnetic leakage, and even tiny air currents have fooled researchers before. These effects can produce real motion while appearing invisible at first glance. This is why extraordinary claims face intense skepticism. The concern is not that new physics is impossible, but that old mistakes are very easy to repeat. Another reason for caution is the shadow of perpetual motion. Any device that appears to create motion without an obvious exchange of momentum raises fears of unlimited energy. Even if energy is supplied electrically, the idea of producing continuous thrust without loss triggers alarms. Physics has never confirmed a machine that can bypass these limits. When past designs hinted at similar behavior, they eventually collapsed under stricter testing. One well-known example is the M drive, which once produced measurable thrust signals in laboratory settings. At first, the data looked promising enough to attract serious attention. Later studies revealed that the signals came from experimental noise and unaccounted interactions. The lesson from that episode still shapes how scientists respond today. It taught the community that early measurements can lie, even when taken in good faith. Because of this history, skepticism is not hostility. It is a form of protection against self-deception. For researchers, accepting a false effect can waste years of effort and distort future work. Rejecting a real effect too early, however, can delay discovery. That balance is what makes this debate so tense. Supporters argue that the system has been tested under increasingly controlled conditions. Critics respond that control must be absolute before conclusions can be drawn. Both sides agree on one thing: the burden of proof is extremely high. Claims that touch foundational laws must survive not just internal testing, but independent replication. Until that happens, the idea exists in a narrow space between possibility and error. This is why the scientific response has been cautious rather than dismissive. No law has been declared broken. No discovery has been accepted as fact. Instead, the claim has been placed under observation. This careful pause is not a dead end. It is the stage that determines whether an idea fades quietly or forces a deeper re-examination of how motion truly works. That pause naturally leads into the next part of the story, where similar attempts from the past provide context for why caution exists and what makes this case harder to ignore. This claim does not exist in a vacuum because science has seen similar moments of excitement before, followed by disappointment. One of the most famous examples is the M drive, a device that promised thrust without propellant and briefly captured global attention. Early tests appeared to show small but measurable force, and even respected labs reported signals that looked real at first. The idea spread quickly because it offered a shortcut around the limits of rocket physics. If true, it would have changed space travel almost overnight, but as testing improved, those signals slowly unraveled. Researchers found that thermal expansion, electromagnetic interaction with test equipment, and vibration were creating false readings. When experiments were redesigned to remove those effects, the thrust disappeared. By the end of deeper investigations, the M drive was no longer considered a real propulsion system. It became a cautionary tale about how easily measurements can mislead, even when researchers act in good faith. Another example comes from the idea known as the quantum drive, which is tied to the theory of quantized inertia. This concept was proposed by Mike McCulloch, who suggested that inertia itself might arise from interactions with distant cosmic radiation. Under this view, thrust without propellant might be possible under very specific conditions. Some startups claimed to build devices based on this idea and reported consistent force in controlled tests. Those reports sparked interest, but they also triggered strong criticism. Many physicists argued that the theory lacked solid experimental support and conflicted with established understanding. So far, no independent verification has confirmed that quantized inertia can produce usable propulsion. These cases shape how scientists react today. They show that unusual results are not rare in early experiments, but lasting effects are. They also explain why bold claims must survive layers of testing before being taken seriously. The project linked to Charles Buhler enters this landscape with both advantages and risks. On one hand, the team is clearly aware of these past failures and often references them as warnings rather than inspirations. They emphasize controlled conditions, careful measurement, and repeatability. On the other hand, history teaches that awareness alone does not prevent error. False effects can hide in places researchers do not expect. What separates this case is not that it avoids comparison, but that it invites it. Instead of claiming to overthrow physics, the work positions itself as an investigation into whether something subtle has been missed. That framing does not prove the idea is correct, but it explains why the scientific community has not dismissed it outright. Every major failure in this field has sharpened the tools used to test the next claim. Those tools are now sharper than ever. This context matters because it sets the bar. Any new propulsion concept must outperform not just theory, but decades of caution. Understanding these past attempts helps explain why skepticism is strong and why patience is required. It also prepares the ground for the next stage of the story, where the focus shifts from comparison to consequence and from caution to what would truly change if this time the effect survives. If this system proves to be real, the first changes would appear quietly, not through dramatic launches or sudden breakthroughs. Satellites would be the earliest place where such a technology could matter, because even small and steady thrust can have large long-term effects in orbit. Today, most satellites carry limited fuel, and once that fuel runs out, the mission slowly ends. A propulsion system that relies only on electricity could allow satellites to adjust their position for years longer than planned. That alone would save billions of dollars and reduce the need for constant replacements. Over time, it would also change how satellites are designed. Engineers would no longer need to reserve large sections of mass for fuel tanks. More space could be used for sensors, communication equipment, or power systems. This shift would not be fast, but it would be steady and hard to reverse once proven reliable. Beyond satellites, the implications for spacecraft design would be even deeper. Current space missions are shaped by fuel limits from the very beginning. Every maneuver must be planned around how much propellant remains. If a spacecraft could generate thrust continuously using electricity, mission planning would change completely. Paths could be adjusted gradually instead of relying on brief and expensive burns. Travel would become slower but far more flexible. This would not replace rockets at launch, but it could redefine everything that happens after reaching space. The impact would extend beyond science and exploration. Space is not only a scientific domain, but also a strategic one. Control over orbital positions affects communication, navigation, and surveillance. Any technology that allows longer presence and finer control in space carries political weight. That is why such ideas attract attention from defense and security planners, even before they are fully proven. History shows that technologies with strategic value are often studied quietly long before they are announced publicly. Energy use would also become a central topic. A propulsion system powered by electricity would tie movement directly to power generation. This would increase the importance of solar arrays, nuclear sources, and energy storage. The question would shift from how much fuel a vehicle carries to how efficiently it can manage power. That change alone would influence decades of engineering priorities. At the same time, caution remains necessary. Even if the effect exists, it may be small, fragile, or limited to narrow conditions. Many technologies work in theory but fail under real-world stress. Radiation, temperature swings, and long-term material fatigue could reduce performance. This is why no agency would rush to adopt such a system without years of validation. Still, the possibility itself is enough to keep attention focused. If confirmed, this would not be a single invention, but a doorway. It would open a new category of propulsion that sits between physics and engineering. The real change would not be speed or spectacle, but control. Control over time, position, and endurance in space. And that is precisely why the next step matters most, because the future of this idea depends entirely on whether it can survive the harshest tests science can apply. At this stage, the future of this idea no longer depends on theory or reputation, but on verification. The next step is testing that removes as many unknowns as possible and places the system in conditions that cannot hide mistakes. For propulsion research, that environment is space. On Earth, even the best laboratories struggle to isolate every interaction. Gravity, vibration, temperature shifts, and electromagnetic noise all introduce effects that can mask the truth. In orbit, many of those variables disappear or become easier to control. That is why space-based testing is seen as the turning point. If the effect vanishes in orbit, the explanation likely lies in Earth-bound interference. If it persists, the conversation changes immediately. Independent testing is just as important as the location. Results must be reproduced by teams that did not build the device and do not share the same assumptions. This process is slow and often frustrating, but it is the only way science protects itself from false breakthroughs. Many promising ideas have failed at this stage, not because they were dishonest, but because early confidence replaced careful doubt. Verification also requires clear limits. A real effect must show consistent behavior, predictable scaling, and boundaries where it stops working. Without those features, engineers cannot design systems, and scientists cannot model outcomes. Even a small but reliable force would matter more than a large but unstable one. That is why researchers focus less on performance and more on repeatability. Another critical factor is transparency. Methods, materials, and measurements must be open enough for others to challenge them. This does not mean revealing every detail to the public, but it does mean allowing serious scrutiny. Science advances through disagreement, not agreement. Every objection strengthens a claim if it survives. Every unanswered challenge weakens it. The line between experimental error and discovery is often thin. History shows that some of the most important findings began as uncomfortable results that refused to disappear. It also shows that many convincing illusions lasted long enough to mislead entire communities. Distinguishing between the two requires patience more than belief. This is why the scientific response so far has been careful rather than celebratory. No laws have been rewritten, no conclusions have been declared final. The idea remains under observation, suspended between possibility and mistake. That suspension is not failure. It is the process working as intended. Only through time, testing, and independent confirmation will it become clear whether this system joins the long list of abandoned concepts or marks the beginning of something genuinely new. Until then, the most important outcome is not an answer, but a method that ensures whatever answer arrives can be trusted. This story is not about belief or disbelief, but about how science confronts the unknown. A device that claims thrust without fuel challenges old assumptions, raises hard questions, and forces careful testing. History warns us to be skeptical, yet progress demands curiosity. Whether this idea fades or survives will depend on evidence, not excitement. Until then, it remains a rare moment where physics, risk, and possibility quietly collide.